Observatory of Strasbourg. And I work mainly with Nicolas Martin, Rodrigo Ibata, and Jen Wan. So today I'm going to present you the determination of Andromeda's dwarf galaxy detection limits, and also the determination of its global properties. So, okay, so why are we interested in dwarf galaxy? So dwarf galaxy are really sensitive to cosmology and to the physics of galaxy formation. As an example here, on this graph, we can see the cumulative number of satellites in function of the infall mass. And we can see that the total number of dwarf galaxy is sensitive to the type of dark matter you use. So here's the different dark matter, so-called dark matter and one dark matter. So it's important to compare simulation with the observation in order to use the dwarf galaxies as cosmological probes. So here, for example, we can constrain the mass of the dark matter. But in order to do so, one must have a great understanding of the detection limits of the observation. So that leads us to a large photometric survey, which resolves stars, such as Panda. So Panda observed from 2003 to 2011 at the CFHT with megacam. It observed over 400 fields of 1 square degree each, centered around the M31 and its companion M33. So that results in a projected radius of around about 150 kiloparsec. So the survey includes 26 dwarf galaxies, and in those 26, 19 were discovered by Panda. So a few of them are circled here, but not all dwarf galaxies are detected. So for example, if we take the galaxy circled in red and we put it in the giant stream over there, the question is it still detected? And that was the goal of this work. So to obtain the detection limits in order to infer the global property of the satellite system. To do so, we had to simulate artificial dwarf galaxy. So this is an example of the CMD as it is pushed through the process. So in here, we only show a red giant branch star at the distance of M31, because the search algorithm for dwarf galaxy only cares for Bragg star. So I show the E magnitude in function of the color, and the first panel is actually stars that are drawn from the isochron and the luminosity function. Then we add photometric uncertainties, which will broaden the curve and the completeness as not all stars are observed. Finally, we insert the dwarf galaxy on an empty field of the survey. And we can compare the fourth panel, which is this CMT, with the one of Andromeda 14, which have similar properties. And we can see that both CMD are closed. So we simulated roughly 500,000 dwarf galaxy with different magnitudes, different size. And then we ran the algorithm by Martin and al. 2013 to know whether or not those dwarf galaxies were detected. This results in nearly 100,000 CPU hours. So those are the results for the field LT1. So this is a field near the halo, but without halo structures. So the x-axis is the magnitude, y-axis is the size of the galaxy, the Alpha radius, and the color code the recovery fraction of the dwarf galaxy. First thing we can see is that the detection of a dwarf galaxy is dependent on its size and magnitude. So if you go to the bottom right of the panel, bright small dwarf galaxy are nearly all recovered. And the more you go to a larger painter dwarf galaxy, so top left of the panel, the less and less they are recovered. Also here, I represented known dwarf galaxy by the red dots. And we can see that nearly all of them are in a region where all the dwarf galaxies are recovered or in a transition area, which means that the detection limits are coherent with the observations that were made. So ideally, we will want to have 20, 50, 100 galaxies per pixel. but this will result in millions of CPU hours, so we only have 5. So in order to overcome the noise, we fit an analytical model, which is shown on panel 2. And this allows us to compare the detection limits in function of the position in the survey. To do so, we use the surface brightness detection limits. So here, the color code these limits for a galaxy of size 250 parsec. Each point on the panel here represents a field of the survey. And so we can mainly see two things. The first one is that its limit is of order 29 to 30 magnitude per arcsecond. And then we also can see that this limit vary in function of the position in the survey. This can be explained by the fact that there are stars from the Milky Way in the northern part of the survey. And also around M31, there are halo structures. And both those types of contamination degrades the recovery of dwarf galaxy. So yeah, that's the reason why it's vary that much. So now that we have detection limits, we wanted to infer the global property of the system. So we use the detection limit and the observation, so the 26 known dwarf galaxy, to obtain the likelihood of a data in function of a model, which is composed of the probability for a dwarf galaxy to have a certain size, magnitude, and distance to M31. And then all of this is wrapped in a Poisson distribution, which gives us the total number of dwarf galaxy around M31. So thanks to forward modeling, we obtain the global properties of the M31 satellite system. And today, I will mainly focus on the luminosity function. So yeah, we assume the probability to obtain a dwarf galaxy of a certain luminosity to be a power law in function of the luminosity with the parameter beta. So, okay. Here I represent in the full black line the best model we obtain. So for beta equal -1.5. And the blue points are actually the known dwarf galaxy. So why is there such a difference? Firstly, because not all dwarf galaxies are in Panda. So the dashed line here represents the band model corrected for the spatial boundaries of Panda. And then also not all dwarf galaxy can be detected. So if we add the detection limits, we obtain the dashed dotted line, which fits the points there. And one thing interesting is that only 15% of dwarf galaxy are detectable. So the next thing is to compare the beta with the parameter we obtain with known parameters from the literature. So for example, for the Milky Way, Toledo from the beta of -1.9. For M81, the beta is -1.227. And so we can see that quantitatively, those are in the same order. So to summarize, we obtain the detection limits of Andromeda's dwarf galaxy, and we use them to derive the global property of the satellite system. So we infer a number of dwarf galaxy of 142 around Andromeda, while only 33 are known. All this work will allow us to test different things. First, if the anisotropy in the distribution of Andromeda's dwarf galaxy is due to detection limits. We can also test if simulations are compatible with the observation. So finally, this work makes it possible for Andromeda dwarf galaxies to be used as cosmological probes. Thank you.
Thank you very much. Questions? I have a question. Why the uncertainty is so large? 99 plus 99 minus 30?
That's a great question. In fact, we fit lots of parameters, and each one is kind of correlated. So I think if you move a little bit, just a little bit, for example, the slope of the luminosity function, the total number of dwarf galaxies will change at the end in our model.
Okay. One question.
Right. Our question is from Terry Bridges. What are the prospects for detecting more M31 dwarf galaxies in the future?
So I guess if we use, for example, Hubble, and we can go deeper and so obtain more stars. So it will make it possible to detect dwarf galaxies with lower magnitude,